it's awesome.
Just like take them right out.
Rachel, what's wrong?
This movie is stupid.
Why? What are you talking about? It's awesome.
No, it's not. Everything about it is fake.
What are you talking about? It's
Everything.
real.
No, it's not.
Yes.
The characters, the lasers, everything's fake.
The lasers are definitely real.
No. Lasers cannot hurt people.
Lasers can definitely hurt people.
No, they can't. Everything about this is all special effects.
Well, maybe it's special effects, but lasers can definitely hurt.
That's not true.
You guys are fighting. Let's put it to the test.
So obviously we have a debacle here. Do lasers actually cause damage? Well, we are going to put this to the test. We have 3 different ways that we're going to be doing this. 1, we have laser tag. I'm going to destroy Andrea and Rachel. Number 2, we're going to hit up Club Lib, right? Now, we have laser cutters there, big laser cutters. We're just going to destroy that wood. And then number 3, we have a little laser right here because Easter is coming.
Will Rachel and Andrea make it out of the bean cluster, or will they die?
I did not hit it. I did not. This shirt is too baggy.
Dude, it's sweaty in this thing.
So inside of this glass tube here is your laser. Around that laser is going to be water, which you can't really tell because it's completely clear and bubbleless, but that is a water-cooled laser, so it's keeping it cool when it starts to fire. It fires because of an air compressor, so there's an air compressor that will turn on when we actually start to do the laser cutting and engraving. And you'll see it flashing as it's firing. It fires into a mirror here that reflects off a couple of other mirrors before landing right down there. I'm actually burning and engraving your materials and whatnot. It fires onto one last mirror here before going down through this lens and onto your materials. The laser is actually not viewable at all. So what they do is add a red diode light, that's what you're seeing, that combines with the laser, so you can actually see where you're going to be etching, engraving, cutting, and burning.
So here's a neat thing here. If you take transitions lenses and a powerful enough laser, you can shine it through the glasses. And the power of the laser is actually strong enough to activate the chemicals in between the lenses that make the lens turn dark in the presence of the sun, turning them effectively into sunglasses. And in case you thought I was stupid and burn a hole through my glasses, you can see here that the effect fades away after a little bit.
Alright, so before we resolve this debacle, we need to learn a little bit about lasers. The word laser stands for light amplification by stimulated emission of radiation. Lasers have three extremely unique characteristics. First, they're monochromatic, which means that they have a very narrow spectral width, or in other words, they cover a short range of wavelengths. This means that they only emit one color. The intensity versus wavelength graph for a spectral lamp would look something like this, where there's a wide range of wavelengths that are covered. Whereas the graph for a laser would look like this, where there's a shorter range of wavelengths that are covered. The third characteristic is that lasers are highly coherent, which means that the emitted photons are in phase with one another, and so the waves that are emitted add to the incoming waves. So, how exactly do lasers work? First, we need an optical cavity. And to make this optical cavity, we need two mirrors. One that is 100% reflective and another one that's less than 100% reflective that will allow the emitted photons to leave the cavity. The second thing we need is a power source. This power source can be a voltage source or any other kind of power source, but it's going to pump photons in order to bring atoms to a higher energy state. The atoms in the crystal tube are going to absorb the energy in the form of photons, and it's going to bring them from a ground state to a highly excited state. Some of the electrons are going to go from this highly excited state right down to the ground state, while others are going to go down to a metastable region. Now, in order for lasers to work, we need to have something called a population inversion. This means that there are more atoms in an excited state than in a ground state, which isn't usually the case. In order to achieve this in a laser, we're going to need to have atoms that stay in the metastable region for a long time. This means that they have a long half-life. In order for this to happen, we need to have a lot of photons being pumped into the crystal cavity in order to have a lot of electrons that get stuck in this space before decaying. Lastly, we have the concepts of spontaneous emission and stimulated emission. Spontaneous emission is the process that occurs when the photons are first pumped into the crystal cavity. The photons cause the electrons to go to a highly excited state and then decay to a metastable region or to a ground state. The electrons that fall to a ground state are forced to emit their photon. This photon is going to go in any direction, making it random and probabilistic. Stimulated emission is a process that was discovered by Albert Einstein, who wrote a paper on it in 1917. Stimulated emission occurs when a photon interacts with an electron that is in a metastable region. It causes the electron to fall to a ground state, but as the electron falls to a ground state, it emits a photon. The photon that's emitted has the exact same energy level and the exact same direction as the photon that interacted with the electron in the first place. These two photons are going to leave the atom, and as they leave the atom, they will later interact with other atoms, causing it to go from 1 photon to 2 photons to 4 to 8, and so on. This is called a photon cascade. Only the photons that have the exact same energy and the exact same direction as the original photons are going to be added to the photon cascade. In addition, only the photons that are emitted perpendicular to the cavity are going to be able to leave the cavity and be part of the laser. This is why lasers have those 3 unique characteristics that we talked about before.
Let's talk about laser classes. We're going to be testing a few different laser classes on Drew, which is why he needs this protective clothing. So to start, we have our weakest class of laser, which is class 1 lasers. There's absolutely no eye hazard. It's safe for viewing even long-term, intentionally looking at the laser. And these are everywhere, including inside a CD or DVD player. So here we have a class 1 laser, which is shining on Drew, and he's living. Next, we have class 1M. This is a laser that Drew would not want to look at directly, but it still would not harm him if it was flashed on him. Okay, next we have a class 2 laser here. These you do not want to stare into the beam, and unintentional exposure to the laser will hurt your eye in about less than 1/4 of a second. So as we're going, the classes are getting bigger, we're going like down the spectrum this way, so wavelength is getting smaller, but our frequency is getting stronger, hence Drew's extra protection.
Hey, shine me. I'm still safe.
Next we have class 3R and B lasers. So these are bad, which is why we don't have them. They're not easy to get a hold of. You have to avoid direct eye contact and exposure from the reflected and the actual beam. Warning, avoid all exposure for class 3B because you'll hurt yourself. And last but not least, we're dealing with class 4 lasers here, which are the most dangerous lasers that one can get. So with class 4 lasers, you want to avoid all skin and eye contact with the laser. Don't look at the dot, don't look at the beam, don't look at the reflected beam. So with class 4 lasers, we're moving out of the visible spectrum, so you won't even be able to see what's going on. You won't know what hit you, but you would be a little damaged. Okay, that's it, right?
Easter's coming!
He's dripping.
Perfect. All right, that's enough. Okay.
He's melting.
Oh my god.
Sure, no.
Get the lens, get the lens, get the lens, get the lens.
It's far enough away, it'll be fine. All right, Drew, time to put it out.
No, not yet.
Why don't...
The lens.